Okay, good afternoon. Thank you for joining us for this third session of Phylogenetics 101. And thanks again to Martin for helping us out and preparing the slides and things to discuss the basics of phylogenetics. We're very grateful that you could all join us. And remember, if you've missed any of the previous sessions, session 1 or session 2, you can go to our YouTube channel and you will find recordings of the presentations there. So, without much to do, over to you, Mark.
Thank you, Faunus, and again, welcome to you all to our third phylogenetics session. Just to remind you, this is Phylogenetics 101, so it is really entry level. We are not going to discuss the hardcore details of the theory and the mathematics and the statistics. I think the aim for today is to get everyone to a point where you can actually produce a phylogenetic tree and perhaps interpret, well, not perhaps, can interpret it. So for that reason, I'm going to show you one method, and that will be maximum likelihood, because that is a method that's widely used, and I will show you how to do this with the use of IQ3 version 2. There are many other software that one can use. If you can't hear me, just indicate in the chat box so that I can up my volume. And then you're welcome to post some questions. Faunus will monitor the questions and we can discuss it as we go on or after the session. So I just want to get my setup right here to share. So what I'm going to do is to give you some discussion or share with you some slides, and then also go into the command line. And this will be on Mac, but it's the same for Windows, more or less the same, and show you how to do the analysis and how to set up your files. Okay, so I just want to get the things here so that we can start. Seems to be working. Okay, so I was also talked about to you about building a phylogenetic tree, and in the title it was said robust. I have put this in brackets because a robust tree needs a little bit more analysis and using different methods to really get to a phylogenetic framework that is that you can have confidence in. So we will talk about how to build a phylogenetic tree today. And this is in collaboration with the SASSB team. So phylogenetics is, the word just means that we are detecting or trying to depict how organisms or gene copies are phylogenetically or evolutionarily related. So it tracks the evolutionary history of these organisms or genes, and it is displayed or shown in a phylogenetic tree. That is a shorthand showing how organisms or genes are then related to each other. So it's about relationships. There are different ways that you can produce a species tree, which most people are interested in. I do realize that there are some people that are more interested in gene phylogenies, but the principles are the same. So I'm talking about species trees here. If you produce gene trees, say, for example, you want to infer species boundaries, fundamentally it's the same approach. So coming back to species trees, there are 4 ways that can be done. It's either taking multiple genes, produce for each of them a multi-sequence alignment, and then concatenate those alignments into what we refer to as a super matrix. And from that matrix, then one can generate a phylogenetic tree. So that is one way. So it's a concatenation of the data to produce a phylogenetic tree. And this tree can be a maximum likelihood tree, a Bayesian tree, or well, actually not a Bayesian tree, a neighbor joining tree, or a parsimony tree. You can also co-estimate the trees. So what that means is you have your full gene data set. So this is also a concatenated data set, but we have multiple trees generated from this matrix. And these trees are evaluated through a Markov chain. So you have many trees. These trees will reach a place in tree space where they have similar likelihoods, and a majority rule consensus tree is then drawn from those trees. So it's from the data, but we investigate multiple trees, and then a summary tree is then drawn from those multiple trees. Those trees are what we call trees in tree space that have high likelihood. So it's a high density probability. We also have site-based analysis that make use of quartets. I'm not going to talk much about them. And then an alternative way of generating a phylogenetic tree, and that's linked to coalescence, is by producing gene trees. So for each gene, you have a phylogeny. And from that phylogeny, a summary tree is generated with software like Astral. So that's different from co-estimation, because here we have a gene tree. So there are multiple gene trees, and then we get a summary of trees. So that tree is then a super tree, in contrast to our super matrix on this side. By the way, these figures were taken from the Astral software manual. So it's a nice manual to read. Okay. Broadly speaking, we can divide phylogenetic inference methods into two categories: the distance-based methods and the character-based methods, which is also referred to as discrete methods. The distance-based methods, most people are familiar with. That's, if you think about neighbor joining, you draw a neighbor joining tree from a distance matrix. So you have your sequence alignment. From the sequence alignment, a distance matrix is generated. And then from the distance matrix, a UPGMA tree or a neighbor joining tree is then constructed. On this side, we have character-based methods. So they take the sequence alignment, the sites, and then infer a phylogeny from the sites. There are three main methods: maximum parsimony. Sorry, let me just say that again: maximum parsimony, maximum likelihood, and then Bayesian inference of phylogenies. So they work directly from the characters, from your alignment. So I'm just going to talk a little bit about each of these methods, just to give you some broader insight, but I am not delving into the details. So character-based methods, I've already mentioned that the most popular method is perhaps the neighbor joining. And I've already explained that you need a distance matrix. So the matrix make use of a genetic distance. The genetic distance can be directly from your sequence, meaning what I'm trying to say is it could be the ratio between the substitutions or changes versus the total length of your sequence. So that's a basic P distance or genetic distance. Of course, these matrices can also be calculated based on a nucleotide substitution model, like the Ducanter model or the HKY, the Hasegawa-Yano 85 model, or Felsenstein's model, or the GTR, the general time reversible model, with gamma, without gamma, with invariable sites, or without invariable sites. It's very quick, so typically we would use it to get a good quick understanding of our phylogeny. So if you want to make sure that there's no problems with your sequence alignment, this is a very quick method to use just to check if you do not have sequences that just cluster somewhere or group somewhere where you do not expect them to be. For example, if you have two genera, suddenly there's a sequence from a genus that group into a different genus, and obviously there might be a problem with your sequence alignment or the sequence that you used. So it's a quick method, but they perform poorly when you have distantly related species. And this is because large distances are hard to estimate, and it also causes a problem by summing up the branch lengths on the path between the species on the phylogeny when defining these pairwise distances. So it's a quick, easy method. You can use Mega. For those of you that are a bit longer in this phylogenetic sphere, Pulp, so the software Pulp can be used, and various others, other software. If you look at the character-based methods, the three, parsimony, Bayesian, and maximum likelihood, as I've already mentioned, they look at the characters and how the characters change across the sites. So for this method, the tree topology that is taken as the best topology is the tree with the smallest number of changes. So what do I mean with that? So here, and this is really just a very, very simple example, we only have 4 taxa. So therefore, there are only 3 different ways that you can rearrange these taxa, rearrange the relationship between these taxa. These sites are informative sites because there are 2 character changes shared by at least two taxa or species. So if we can consider character 1, so character, when I say the word character, it means site. It's equivalent to site. When I say character state, it's equivalent to the character type or the character in that site. So just to be correct, so we will use character and character state as the terminology for the site and the type of character at that site. Right. Okay, so character 1. If we plot character 1, so that's A, C, C. So T1, taxon 1 has an A, taxon 2 has an A, 3 a C, and 4 a C. So this is your sequences. These are the leaves. So that is what you observe. Then the most parsimonious character state at the ancestor of T1 and T2 would be an A, because that doesn't cause a change. For T3 and 4, it would be C, because it doesn't cause a change. If it was A, we had 1, 2 changes, and that is against the principles or violates the principle of parsimony. So now we only have 1 change, an A to a C or a C to an A. These are not rooted trees, so we don't know what is the direction of change. If we take an alternative tree topology, so this is T1 related to T3, so they share an ancestor, and T2 sharing an ancestor with T4, you can work out how the character states or how many changes there will be on this tree. So just to explain to you, so we put C there and C there, because that will cause the fewest changes. So you can see there's no change. So now we only have one change, C to A and C to A here. So that in total brings us to 2 changes. And the same principle applies to the third topology, tree topology. So that was for one character with 2 character states. If we look at the second character, it is the same principle. We have T and T, C and C, and one change if the ancestral state is T and the ancestral state is C for T3 and T4. For this topology, it will work out to 2 steps, and the same for topology 3. So the number of changes over the tree is then just the sum of the number of steps or changes. So for tree topology 1, it will be 2 steps. For tree topology 2, it will be 4 steps, and for tree topology 3, it will also be 4 steps. So the most parsimonious tree for this data set is then tree 1. Parsimony is intuitive, it's easy to understand. I just want to quickly come back to the informative sites. If it's a constant site, there's no information. If it's a unique change, so one character change and the rest is constant, that will just cause a polytone. So there's no information in terms of the evolution and relationship of these trees. Right, hope you're all with me. Let's move to just a final thought. So in parsimony, the model is not stated as in maximum likelihood and in Bayesian analysis. So we do not have a substitution model. You can, of course, add a character weight matrix. So then it's a weighted parsimony. But generally, there's no process of evolution incorporated into this method. One of the problems with parsimony is that you often end up with many parsimonious trees. So these are all trees with the same length, and all of them are equally valid. Another problem, and that is perhaps one of the biggest problems, so many trees is a problem because you have to interpret it, you have to talk about it. But an error that can be caused in parsimony can be through long branch attraction, and we will come back to long branch attraction. Just perhaps quickly to say, that is when long branches are literally attracting each other, and then you get the wrong phylogeny. Maximum likelihood is a statistical analysis, and it's based on probability. The outcome of a maximum likelihood is a maximum likelihood tree with a maximum likelihood value. So here we ask, what is the probability that I would observe this sequence given our tree topology and the process of evolution? So this is a substitution matrix. There we have base or nucleotide frequencies, and we have a gamma distribution that is linked to rate heterogeneity among sites. So we want to know what is the likelihood of this data given this information. So what happens in a maximum likelihood is the program starts with a tree. That is your starting tree. And it can be a parsimony tree or a neighbor joining tree. What it does then is to calculate the likelihood value of that tree given our substitution model. The substitution model then produce the branch lengths, the tree topology, so how it is related, how the taxa are related, and that likelihood is then stored. Then the program changes the topology, and that change can be introduced through, or can be made rather, through branch swapping. And there are different ways that branches can be swapped, different organisms. It calculates the likelihood of that specific tree topology, so this one, and the branch length is then also included. If that topology has a better likelihood, then that topology will be taken as the best likelihood. And so it will go on until it finds the tree in tree space, so the tree among all different topologies that has the best likelihood. And then that is your maximum likelihood tree. And of course, you can randomize it so that you find an optimum likelihood instead of a local likelihood. The last method is a Bayesian approach. So it's again a statistical approach based on probability, but this results in a posterior probability of topology. So it relies like a maximum likelihood on a likelihood function, but here we also include a prior probability. So something that you know or believe. That is then part of your Bayesian theorem, and the output is a phylogenetic tree based on the majority of the trees that has similar topology and likelihoods. So in a Bayesian context, we ask what is the probability of our data, of our tree, given the data. So it's slightly different from maximum likelihood in the conceptually, because we ask now what is the probability of that tree topology, given our data. We analyze many trees in tree space, and we take the summary of the trees that is in that space that all has very similar likelihood. So therefore they have similar topologies, similar parameter values, so similar to tree branch lengths and so on. Okay, so these are the three basically the three methods: parsimony, maximum likelihood, and Bayesian inference of phylogenies.
Okay, I think let's hear, before we continue, if there are any specific questions that you would like to ask about this. I think this is a good point where we can ask. If there's anything, please either type in. It's the easiest if you type in your question, or if you have one and you want to sort of make a voice note, sort of in time voice note, raise your hand and we will allow you to ask that question. So any questions you want to pose, please do so. And I think we can continue, Martin.
Great, okay. In the past, I think in the past sessions, we talked about outgroups. I just want to remind you what an outgroup is. So that outgroup is a group of species, species, that serves as a reference point to determine the evolutionary relationships among the in-group taxa. So the in-group taxa are those taxa that you are interested in, trying to study, interested in their relationships. So the purpose of the outgroups is to root the phylogenetic tree. It polarized character states, as I've explained in my small little demonstration about the phylogenetic trees in parsimony. We don't know what is the direction of change, so by adding your outgroup and then root your tree against the outgroup, you can infer which are ancestral states and which are derived states. So plasmorphic states or apomorphies. We can distinguish homology from convergence, and in overall, it increased the tree accuracy. These outgroups must be not too distant. So if you want to infer the phylogeny of a group of species in a genus, I would not take an outgroup from another order. I would rather take a species or group of species that's in a genus that you know is sister to the genus that you are investigating. If you go back to our first session, we talked about sister groups, monophyletic groups, paraphyletic, polyphyly, and so on. So just to remind you, a sister group is the group, the monophyletic group next to our study group. But it must also not be too close. If it's too close, it may not represent a true outgroup. And what happens then the in-group or the outgroup taxa, depending on your selection, wants to go into the in-group. So that causes problems with your phylogenetic analysis. It's also advisable to use more than one taxon if possible, and to select this outgroup based on prior knowledge, blast searches. So you take your sequence, blast it, and try to take sequences that has higher similarity with your in-group taxon. Phylogenetic analysis can also be done, including a number of possible outgroup taxa. And to give you some advice, it's good to take different outgroups and test the effect of these outgroups on your phylogeny. Because sometimes you choose an outgroup and that outgroup wants to jump into the in-group, so you have to remove that. Just a word about not too distant. If it's too distant, it causes noise in your data set. So it results into topological errors because much of the information can be erased if you can imagine if it adds something that's distant. Now I just introduce a lot of, we can say, random changes or differences, variation in your data set. And that causes then error in the topology or the phylogenetic result.
On the topic of outgroups, there's a question from Martin. He says, generally speaking, what is your opinion on selecting midpoint routing instead of an actual outgroup?
That is a good question. So I would not advise midpoint routing unless you do not have a choice. So there are scenarios where you have to use a midpoint because there's just no outgroup. In the context of gene phylogenies, so if you want to look at how genes evolve, so we're talking about paralogs now, then often you can't add an outgroup because that outgroup is just going to jump somewhere into the in-group. So in that case, midpoint will be used, at least in my opinion. So I would steer away from midpoint unless it cannot be avoided. So for those of us, for you in the audience, the midpoint routing is just the longest branch divided into that becomes your routing.
Then there's another question here about a more general one. For a normal phylogenetic study, is it necessary to do all approaches, maximum sparsity, likelihood, or is some better than others for producing a publication-ready phylogeny?
That is a good question. So first of all, I don't think there's the best method. All of them have their pros and cons. Sometimes it is impossible to use a specific method. You can imagine if you have 1,000 taxa, parsimony, it takes a long time. So it will be, or if you have a very large data set and many taxa, parsimony is going to be very difficult to use because it will take forever. And even with small data set, it says it can take a very long time. But it also depends on your question. If you want to know how taxa group in the context of parsimony, you might use parsimony. If you're not interested in that and you just want to, or you do a phylogenomics analysis, then you will use maximum likelihood, especially something like IQ3. So if you want to get a quick look, you will use neighbor joining. I think it's just important to try to use more than one method so that the one method can support the result of the second method and vice versa. Let me rephrase this. So that the one method can give support to the second method. So if you have congruent trees or topologies that are the same, generated from two methods or more, then you have more confidence in the topology. Of course, you'll also add your bootstrap values. And if you do Bayesian analysis, your posterior probability values. So it really depends on your data, it depends on your question. There are certain cases where we would like to use parsimony, especially if you want to look at character state changes, but you can also do that in maximum likelihood.
Okay, I think you can continue.
Okay, so let's move now to a practical application and the use of maximum likelihood. So I make a lot of assumptions in this session. I make the assumption that you have investigated your chromatic graphs, that you have checked your alignments, that you're familiar with your question, that we are actually at a point here where we can generate the final phylogenetic tree. So this diagram was presented in the second session on 27 November. So if you want to go and look at a YouTube video, I've explained all of this in detail. So we make the assumption that your data structure is good, you're happy, you can go. So broadly speaking, the steps involved in a maximum likelihood analysis are as follows. You start with your data, you then get a substitution model for your sequence, and this is a model that is determined for each data set. So for each data set, you use J-model test to get your substitution model, or probe test if it's an amino acid sequence data, or you can do this in the program that you use. For example, IQ3, you do not need to do any analysis prior to your maximum likelihood analysis. The model test is incorporated in IQ3, and you set the program to do it for you. So of course, it will first determine the substitution model, and then do the maximum likelihood analysis to get the maximum likelihood tree. So there are two ways that you can do it. Prior your analysis with a different software, such as J-model test, or in the software that you use, such as IQ3. Once you have your model, and we will have later a session on substitution models, so that you can better understand what these models do and what they mean. But for this session, it is just good enough to know that there are different substitution models, and we incorporate these models in our analysis. Once you have the substitution model that should be applied, then we start with our tree search. We search tree space for the tree that yields the maximum likelihood. And just a reminder, tree space just means all the different tree topologies. The way that your tree topology changed or is changed in the analysis is through these branch swapping methods. And there are different methods that have different names, referring to the way that the branch is swapped. So you get nearest neighbor interchange, where people take a neighbor clade and just swap it. You get sub-tree pruning and reconnection. It takes a sub-tree, cut it, put it somewhere else, and then TBR is just a combination of these two. TBR stands for tree bisection reconnection. So in IQ3 or some other programs, they refer to TBR as the best combination of the two. And this is something you can set. Typically, people just use the default, which I think normally is NNI. Now we search tree space, get maximum likelihood values for each tree in tree space. And finally, it reaches a tree where it doesn't matter if you go change the topology, it doesn't get a better maximum likelihood. So that is then the tree with the best max likelihood. And this, by the way, so that you just remember this, we are not searching the full tree space, not each and every tree that is possibly in that space. Because that will take eons to do. For 10 taxa, there are thousands of trees. For 20, I've asked ChatGPT to give me the value of 100 taxa, and it told me I cannot do it because it will take too much of its power. So there's trillions of trees, and we cannot do that. So there are optimization functions in these programs that might use hill climbing methods, different types of methods to do a heuristic search or heuristic analysis, which means that you might end up in a local optimum, meaning a tree with the best likelihood, but somewhere in tree space, there might be a better tree. You can randomize the analysis. There are different ways the programs does it. So just so that you know. Right, okay. Now, a tree with a topology, but without any confidence support is basically useless. And I say that carefully, because I know this is recorded, but we need statistical support for the nodes. Because if you do not have it, your nodes, your branches can collapse. So although you have a phylogeny, there's no statistical support, or if you do not have support, you do not have confidence in how these taxa are related. And there are different ways in maximum likelihoods, and specifically IQ tree. We can do an ultra-fast bootstrap analysis, and I will talk a little bit about it, supported by Shimodura Hasegawa. And what's a full name? Likelihood ratio test. And then the full bootstrap analysis, as we know from Felsenstein's paper, Felsenstein 1985. Oh, sorry, it's the Shimodura Hasegawa approximate likelihood ratio test. Now we'll just say a little bit about it later. So again, another assumption that I make is that I assume your data has phylogenetic signal, and that you can combine your data sets. Just to be reminded that you cannot combine all the data sets, just combine them, because there might be data that cause incongruent topologies. And there are methods that we can use to test it, but that's not in the scope of this session. Right, because I would really like you to do produce a phylogenetic tree at the end of this session. Right, so, okay. Now, how do you combine data and fast for your analysis? There's a program that one can use called FastConcatG. If you use IQ-Tree, you can also keep your files in a separate folder. So these are the multi-sequence alignments of your genes. And then you can tell the program it must use the folder and take the sequences and then use or construct a concatenated data set. But I will show you how to use FastConcatG. What do you need? Sequences must be aligned. So if you have ITS, that data set must be aligned. If you have translation elevation factor 1 alpha, it must be aligned, and so on. The files can be in Nexus, Philo, or FASTA format. Very important is, and that goes for any program that you use, the sequence names must be identical, because it reads the sequence name, link that sequence name with the sequence in all the different files. You do not need a complete sequence data set for all the genes. You can have, say, a data set that's complete with all the taxa, and then you have variation like the TEF, translation elevation factor. TEF has 1 missing, beta tubulin might have 2 missing, so we create a concatenated data set, which we refer to as a Swiss cheese data set. Swiss cheese because it has these holes. It is a command line program, so it runs from your command line. So for Windows, it's command prompt, and for Linux or Mac, it's the terminal. You can download the program from this website, and you must have Perl installed on your PC. So for the Windows users, you can use Strawberry Perl. But just go on the Perl website, so that's a program language, download it and install it on your computer. So I'm going to show you now how to use it. Need to get out of my. Okay, I hope you can see there. It's a bit small for us here in the room. Right. Okay, so I've already downloaded FastConcat. So in Linux, if you type ls, it will list the files in that folder. For Windows users, dir, as in directory. dir, type it and press enter, and then you will see a list of the files. Now, of course, you must be in the folder where you want to work. I've already put myself in the correct folder, but just to show, in both cases, Windows and Linux, you use the command cd, so change directory. In Windows, you can go to the top part of your where it shows all your files in Windows, and copy the path, paste it into your terminal. For me, it's easy. I just drag the folder where I want to work, or the directory, into my terminal after cd space. If I press enter, I'm now in the correct folder, and it tells me I'm in the correct folder because it says there IQ2. But that's not where we want to be. We want to be in the FastConcat G folder, because that's where the program is that I want to use. So I clear this. Okay. Now I have a little problem because I deleted. No, I'm in the wrong folder. Sorry. I want to be in this folder. Okay. So what I did here was to take the FastConcat file. You can see it has the extension PL for Perl. I just changed the name so that it's a bit more shorter. And I have my 3 data sets here. These are genes from the mitochondrial genome, cytochrome C, large subunit, and small subunit. So if I want to concatenate these sequences, and remember the names must be exactly the same in all of these files, I activate the program, and I can use tab, same in Windows, to autocomplete the name of the program that I want to use, or the file. So if I now type in Perl, so that's the program language, or the language that you use, space FastConcat, that's the program written in Perl. And I press enter, it will open a window. Now you can see this is not a program where you can click and change something. You have to use letters, your keyboard, to change the parameters or the settings. So first of all, I want to change, it says here, Nexus. No, if you want to use a Nexus file, get a Nexus file, you type in N, press enter. Now we have a block. Now we have a Nexus file that can be used in Mr. Bayes. So you can use this program not only for maximum likelihood, but also to generate files that can be used in Mr. Bayes for a Bayesian analysis. Then, what else do I want to use? I want a partition file. That becomes important when we want to partition our data. So you will input into IQ3 the concatenated data set, but you will also add a partition file that tells the program from where to where is one partition, from which character to which character is the second and third and so on partitions, because you want to apply models that is unlinked for each partition. So although it is the same model, a GTR, the values are, the parameters are unlinked, so they can get unique values for each partition. Right, okay, so that would be How do I know what key to type? It tells us, for example, if I want a partition, type L and enter. So if I type L and enter, now you would see that the partition file is set to supermatrix. If I type L and enter again, it says no, and that is what we want. Okay. I'm going to keep a raster file because that's the file I use in IQ3. And then how do you get your output? Just type S and enter. It says here start fast concat, type S and enter. So that's what we're going to do. Enter, and now I am very happy because it tells me that for this taxon, there are 3 files, for that taxon, there are 3 files, and so on. So if you have sequences with different names, it will give you the output, tell you what's the sample taxon names. So for example, if you have in one data set mystic, let's make it something that's easier to pronounce, Delphis, and you have Delphis in another one without the S, you will see that there's 2 files, and then Delphi without S, 1 file. Okay, what do we get in our output file? What output files do we get? First, there's an Excel spreadsheet that shows the number of partitions and their ranges. Start position, end position, and so on. It tells you how many informative sites there are. So this will be parsimony informative sites and all kinds of information about your data set. What we really want to use is actually the partition file. So this file, it's now very small. Oops. It's gone. But I will show you a slide where it gives us the ranges. So cytochrome starts from 1, ends at 44, character 44, LSU then of course 45 to 160 and so on. Okay, so that is what we're going to use. So the 2 files you are going to use in your analysis will be the partition file, which I am just changing to partition, so it's short, and then the concatenated file, which is this one that says supermatrix. So I'm just going to call it combine fuss. Right. These files has to be copied in the folder where you have IQ3, unless you know how to create a path to the program. So if you know how to do that, I think in Windows, it automatically creates a path to the program, but on Macs and Linux, you have to change the settings, your environmental settings, so that you include the path to the program so that you can execute it without typing certain things that I will show you to activate it. Okay. Then, if you have a path, you can also do the analysis from any directory, so it makes it much easier. But I know I have not set the path here on my Mac, so I will copy the files that we need into the folder. Oops, a bit confused. So that file will go to I'm just going to delete these files. I'm sorry, I got a little bit confused with what's where. But that's not a train smash. So now I have my data file and my partition file in the same folder as IQ32 because we're going to use IQ32. Okay, we're running a little bit late. May I continue?
Yes, I think so. What are we?
So next part is how to use IQ tree.
I can continue.
Yeah, because there is also a message from the student reps that in 2 weeks' time or so, they're going to take the people again through this.
Right.
So I think, if you can give a good overview so that people can prepare,
Okay.
we'll continue.
Okay, so we will use IQ-Tree. There is a web server for IQ-Tree, but I would encourage you to use the command line. The web server, of course, is easier to use, but it takes a while for your analysis because your analysis is queued, and depending on the number of analyses that's in front of you, you might wait quite a long time. I did something yesterday just to test this, and I waited until this morning, and I started yesterday morning. And really, the IQ-Tree, the software documentation, the manual is well documented and well updated. And as you can see, the latest release was on 7 February 2025. So it's an active community, active software development, people that write a code, and it is frequently updated. Okay, so this is what the online version looks like. I'm not going to spend much time here because it's more important to show you how to use the command line. The student group might also be able to show you how to use the online version. But if you know how to use the command line, it's easy to use the online. Okay, so what do we need for IQ-Tree? Both command line and online. You need your multiple sequence alignments in compatible format. This will be FASTA, Phylum, or Nexus. If you want to generate a species tree from a super matrix, you have your concatenated sequence alignment, either using FastConcat or IQ-Tree 2. And you need your partition file to tell the program what the range of where your partitions are. If you want to produce a super tree, there is a function in IQ-Tree that can generate gene trees, and these will be stored in a folder, and from that folder you can also generate a summary tree or then your super tree. It works on Mac OS, Windows, and Linux, and please read the manual. This is now one time you really need to read the manual because there's a lot that you can do in IQ-Tree, and it's impossible to cover in the time of this given to this session. So, if you forget everything, read a manual. Okay, your partition file can be in two formats. Directly XML format, as was given to us, or output from XML. So it starts with DNA because this is DNA sequence data, comma, space, and then a name for the partition and a range. Or in the Nexus format, which starts with hash nexus, begin sets, a name for your character set, the range, so on, and end. But I don't want to spend time here because we get it from XML. This becomes important for Bayesian analysis because there you also want to partition your file. I also want to partition your data. And here's the commands that you will use. So let me explain what it means. So we talk about these -s-p as flags. So that is the function that you can change or the setting that you can change. Set your input file, set your output file, and so on. So the command is as follows. So IQ-Tree is the program. -s is your sequence file. So that's the input. It's a lowercase s. There's an uppercase s, it has a different function. -p is the partition file name. If it's capital P, it will refer to your directory. So you will not use a file name, you will use a directory name. -m refers to the model. And here we tell the program, please infer the model per partition for us, and then make a phylogenetic tree for us. So it is the model, so dash N, and the model here will be not stated, but inferred. If you know what's the model, you can use the model, GTR, for example, plus I plus G. Look at the manual to see how that is then set. Dash B, uppercase, is an ultra-fast bootstrap, and I don't think we will have time to discuss this. So that will be a nice topic for next session. And this is their reps, 1,000. When you do ultra-fast bootstrap analysis, you must complement it with the approximate likelihood ratio test. There is the one that I talked about, the SHALT, ALRT. So it's dash ALRT and the number of reps. If you want to do a proper bootstrap, you will change the uppercase B to a lowercase b, and then set the number of reps. For the purpose of this demonstration, I will use an ultra-fast bootstrap analysis, but for publication purposes, and then depending on the size of your data set, you will do a proper bootstrap. Okay. Now, to get myself out of this. Let's go back now to our command line. Okay, so where am I? I am now in a folder called command combined data. Where do I want to be? I want to be in a folder where I can do the analysis. So I'm currently in the original FastConcat-G, in the folder where I use FastConcat-G. If I type in cd, same for Windows, space, ... it takes you one up in the hierarchy of your folder structure. So now I'm in the SASPB session there. If I type in LSL, no, it lists the folders. I want to go to ML analysis. I use stab to autocomplete, so it makes it easier. And then let me just clear all of this nonsense. Okay, we have 3 files there. IQ3, the program, combined the data set, and then the partition file. So now you can be lazy and copy and paste the settings, or you can copy and paste it in a text editor. That's going to be there in a text editor. Such as the one that I have here, and then paste it in your command line. So there are different ways of doing this. Now, if you install it in Windows, it will automatically be, I think it will automatically have the path. In my case, with my Mac, I didn't set the path, so I must use // to activate the program. And then if you didn't change the file name, you have to set the file name, which in my case is combined data. First, let us just make sure it's true. Yeah, it is the correct name. The partition file, you can notice I cannot use my mouse. I have to use the keys, the arrows. Just close that. I hope you can still hear me. So it feels like my voice is going down. So partition txt. And you have to include the extensions. The extensions are these things, .fuzz, .txt. If you make a spelling mistakes, the program won't see the file. If you didn't include the extensions as it is, the program won't see it. Just change that. So our model, we go to ultra-fast bootstrap, approximate likelihood ratio of 1,000. And hopefully if you press enter, oops, then it doesn't see it. Why? Because we have a spelling mistake. So my spelling is not so great today. I have partial. In this, and I'm showing you this because to show you that if you have a mistake in your command, here, so let's just check this. Combine plus, and there, voila, we are running it. So first, you could see that it was determining the different models for us. And then it did maximum likelihood for us, and the ultra-fast bootstrap and the likelihood ratio test. Okay, so your output is then a lot of files. The file that we use to get our tree is not a con tree. The con tree is the consensus tree from your bootstrap. So that's not a tree that you want to use. The tree that you want to use is the tree from the data, which we refer to as the fundamental tree. So a bootstrap tree is not a fundamental tree, it's a summary tree. For your trees, you will use a program called Phylogeny that you can download from the internet. The reason why you use Phylogeny is because if we open the tree file in, say, a tree editor, you will notice that it's not a typical tree file. It has the branch lengths as well as the bootstrap values and the likelihood ratio values. So if you open it in Mega, it won't open. I apologize for this font size that's so small. I hope you can see it on your screen. Right, so I'm going to change the tree extension to .3. Now, if I right-click on a Mac, you probably can do the same on a Windows machine, or you open Phylogeny on your Windows machine. You can load the file. So this is the tree file. To ask you what is the input, so this is our stats. And there is our maximum likelihood tree. So first I'm going to unroot it. Then I'm just going to make the node labels bigger, the tip labels, so that you can see it. And the node labels, I'm going to select, change it to stats, and increase the font size. Okay, so there we have it. The first numbers are the likelihood ratio values that range between 0 and 1 or 0 and 100%. Typically, it's shown as 0 to 1. So the closer to 1, the more confidence you have, or closer to 100%, of course, you have more confidence. 90 to 100 is strong confidence. And the same with your bootstrap values, which is the second value. In the context of ultra-fast bootstrap, it's 95% and up is taken as strong support. That is lower than that is not considered being supportive of the null or relationship. So I mentioned that, so if you use ultra-fast bootstrap, you use it with ALRT, the likelihood ratio test, the branch likelihood ratio test. They need to support each other, and that is applicable to large data sets, like phylogenetic data sets. Typically, in the case of a phylogenomic analysis, all these values will get close to 100%. So there we will also look at gene concordance factors. So the proper way to do this, because we only have 3 genes, small data sets, is to do a proper bootstrap. but it might take a little bit longer than necessary, longer for the session than the time is allowing me. Okay, so that is really in very short how you would do a maximum likelihood analysis in IQ3. And I would really advise you to read a manual. I'm stating here, the program tells you in the output, you see that from the screen on your command line, what is the program, what is the tree file. So the maximum likelihood tree is the one with the tree file as an extension. The rest are all kinds of files with information that you might want to use. But in most cases, you want the tree file with the support values. Here's the phylogenetic tree. I've already talked about ultra-fast bootstrap support. This was taken directly from the manual. Just to again remind you that ultra-fast is a very quick way of getting a bootstrap value. It uses hill climbing, all kinds of other different types of optimization algorithms. What you get is not a bootstrap value. It is something different. In general, we take values greater than 95 as supported, but you also add your Shimodora, Hasegawa approximate likelihood ratio to support it. But if you are confused about these things, really just do a normal Felsenstein type bootstrap analysis. Okay, I think we can leave the rest, the errors, what caused error, for a later session. There's a couple of slides, but it will take some time. I think it was more important to get you to a point where you can produce a phylogenetic tree, can do a phylogenetic analysis. And if you follow the instructions here, you will really get a phylogenetic tree that's usable. That depends on your data, how good your data is. If data input is poor, if bad data in, bad results. Okay. So I'm going to skip these slides. And then I want to remind you to join the student group in 2 weeks' time for troubleshooting and further discussions. Okay.
Okay, thank you, Martin. There has been a comment or two from Abigail as well in the chat box, where there's a reference to the student session and a link to the WhatsApp group. So please, if you want to join the WhatsApp group so that you get information about the sessions. And then Abigail also provided some information on, why you would like to use the online version. And if you have large data set and your computer doesn't have the power, this is an ideal way of doing it.
And of course, with all this software, once you move into the use of a server, you cannot use interface. So we, with large data sets, bacterial genomics, fungal genomics, phylogenomics, we use servers, and you do that through the command line.
Okay, you want to unshare? Okay, then let's see for a question or two, anything that you would like to ask? If not, thank you very much, Martin. You can still type, but thank you very much for the time that you've spent. We are recording this session and we'll try and post it as quick as possible. So if you've missed something, you want to go back to something that's said, you're welcome. So what I would suggest is that if you want to make proper use of the session with the tutorial with the student, have a look, try making a tree and then get to them so that they can help you with troubleshooting and things. But there's a thank you note in the comments. And if we have nothing else, then I think this is it. Thank you.
It was a pleasure.
And be on the lookout, we will advertise our next session. Probably within the next month or so, we will have a follow-up. And as you've seen from Martin's slides, there's still a lot to discuss. Thank you. And thank
Goodbye
you
all.
to everybody that joined us today.